Hi everyone, I'm Xiaoyuan. In this video, I'm going to talk about SecuredKG, which is a system for automated gathering and management of open source cyber threat intelligence, or OSCTI. We're going to start with an introduction to the OSCTI management background. Then we discuss the architecture of SecuredKG, covering the backend system design, report collection, security knowledge ontology, knowledge extraction, and graph construction. At last, we present a demonstration of a front-end UI built for knowledge graph exploration in SecuredKG and discuss the future direction for this work. Sophisticated cyber attacks have plagued many high-profile businesses. To remain aware of the fast-evolving threat landscape and gain insights into the most dangerous threats, Open Source Cyber Threat Intelligence, or OSCTI, has received growing attention from the community. Commonly, knowledge about threats is presented in a vast number of CTI reports in various forms, for example, threat reports, security news, and articles. Despite the pressing need for high-quality CTI, existing CTI gathering and management systems, however, have primarily focused on simple indicator of compromise, or IOCs, such as signatures of artifacts, malicious file process names, IP addresses, and domain names. Though effective in capturing isolated, low-level IOCs, these platforms cannot capture high-level behaviors such as adversary tactics, techniques, and procedures, or TTP, which are tied to the attacker's goal and thus much harder to change. As the volume of OSCTI sources increases day by day, it becomes increasingly challenging to maneuver through and correlate the myriad of sources to gain useful insight. Towards this end, there is a pressing need for a new system that can harvest and manage high-fidelity threat intelligence in an automated, intelligent, and principled way. There are several key challenges to build such a system. First, CTI reports come in diverse formats. Some report contains structured fields such as table and lists, and some reports primarily consist of unstructured natural language texts. The platform is expected to be capable of handling such diversity and extracting information. Second, besides IOCs, CTI reports contain various other entities and capture threat behaviors. The platform is expected to have wide coverage of entities and relation types to comprehensively model the threats. Third, accurately extracting threat knowledge from unstructured CTI text is non-trivial. This is due to the presence of massive nuance particular to the security context, such as special characters like dot and underscores in IOCs. This nuance limits the performance of most NLP models, including sentence segmentation, tokenization, etc. Besides, some learning-based information extraction approaches require large annotated training corpora, which is expensive to obtain manually. Fifth, how to programmatically obtain annotations becomes another challenge. To bridge the gap, we build SecuredKG, a system for automated CTI gathering and management. SecuredKG collects CTI reports from various sources, uses a combination of AI and NLP techniques to extract high-fidelity knowledge about threat behavior as threat-related entities and relations. It also constructs a security knowledge graph containing the entity relation triplets, and update the knowledge graph by continuously ingesting new data. Specifically, SecuredKG has the following key components. First, a set of fast and robust crawlers for crawling OSCTI reports from more than 40 major security websites. Second, a security knowledge ontology that models a wide range of high-level and low-level security-related entities and relations. Third, a combination of AI and NLP techniques, for example, CRF, to accurately extract entities and relations. Specifically, we leverage data programming to programmatically create large training corpora. Fourth, an extensible backend system that manages all components for OSCTI gathering, knowledge extraction, knowledge graph construction, and persistence. Fifth, a UI that provides various types of interactivity to facilitate knowledge graph exploration. Different from general knowledge graphs that store and represent general knowledge like names for movie and actors, SecuredKG targets automated extraction and management of CTI knowledge for the security domain, which is the first work in this space. Next, we're going to cover the architecture for SecurityKG. So here's a figure for the SecurityKG's architecture. SecurityKG manages the lifecycle of security knowledge in 4 stages: collection, processing, storage, and application. In the collection stage, SecurityKG periodically and incrementally collects OSCTI reports from multiple sources. In the processing stage, SecurityKG parses the reports, extracts structured knowledge, and constructs a security knowledge graph based on a predefined ontology. In the storage stage, SecurityKG inserts the knowledge into backend database for storage. Various applications, for example, threat searching, threat analysis, threat hunting, can all be built by accessing the security knowledge graph stored in the database. SecurityKG also provides a front-end UI to facilitate knowledge graph exploration. We first explain how we design the backend system. To handle diverse OSCTI reports, the system needs to be scalable and maintain a unified representation of all possible knowledge types in both known and future data sources. The system also needs to be extensible to incorporate new data sources and processing and storage components to serve the need of different applications. To make the system scalable, we parallelize the processing procedure of OSCTI reports. We further pipeline the processing steps in the procedure to improve the throughput. Between different steps in the pipeline, we specify the formats of intermediate representations to make them serializable. With such pipeline design, we can have multiple computing instances for a single step and pass serialized intermediate result across the network, making multi-host deployment and load balancing possible. To comprehensively represent security knowledge, we design an intermediate CTI representation and separate it from the security knowledge ontology. Intermediate CTI representation is a schema that covers relevant and potentially useful information in all data sources and lists out the corresponding fields. We construct this schema by iterating through data sources, adding previously undefined types of knowledge, and merging similar fields. Specifically, our source-dependent parser will first convert the original OSCTI report into representations that follow this schema by parsing the structured fields. Then, our source-independent extractors will further refine their representation by extracting information like IOC and malware names from unstructured texts and putting them into corresponding fields. Directly using these intermediate representations results in inefficient storage. Furthermore, these long representations are not convenient for end users. Thus, before merging them into the storage through connectors, SecurityKG refactors them to match our security knowledge ontology, which is separately designed and has clear and concise semantics. To make the system extensible, we adopt a modular design, allowing multiple components with the same interface to work together in the same processing step. For example, SecurityKG by default uses a Neo4j connector to export knowledge into Neo4j database. However, if the user cares less about multi-hop relations, he or she may switch to a RDBMS using a SQL connector. Similarly, parsers and extractors can be switched or extended, making the system extensible. Furthermore, the system can be configured through a user-provided configuration file, which specifies the set of components to use and additional parameters that are passed to this component. To collect the report used in the security knowledge graph, we built a crawler framework that has more than 40 crawlers for collecting OSCTI report from major security sources, covering threat encyclopedias, blogs, security news, etc. The crawler framework schedules periodic execution and reboot after failure for different crawlers in an efficient and robust manner. It also has a multi-threaded design to boost the efficiency, achieving a throughput of approximately 350 reports per minute on a single deployed host. In total, we have collected over 120,000 OSCTI reports, and the number is still increasing. The security knowledge ontology specifies the types of security-related entities and relations in the security knowledge graph. Based on our observation of OICTI data sources, we categorize OICTI reports into three major types: malware reports, vulnerability reports, and attack reports. For each report, we associate it with an entity of the corresponding type. Besides, reports are created by specific CTI vendors and often contain information concepts on threat actors, techniques, tools, softwares, and various types of IOCs. Thus, we create entities for these concepts as well. Entities have a relation between them, as well as attributes in the form of key-value pairs. By constructing such an ontology, we can capture different types of security knowledge in the system. Compared to other cyber ontologies, our ontology targets a larger set. Now, we describe the steps inside the processing stage that extract security knowledge from the collected OICTI report files. The porters take the input report files and convert them into intermediate report representations. They group multi-page reports and add metadata like IDs, sources, titles, and original file locations and timestamps. The checkers work as filters on the list of intermediate report representations. They screen out irrelevant reports like empty pages or ads by running conditional checks. The parsers are source dependent, taking the advantage of prior knowledge of the source website structure and extracting keys and values from report files. They convert the list of intermediate report representations into a list of intermediate CTI representations. The extractors further refine these intermediate CTI representations by completing some of the fields using entity recognition and relation extraction. Since the intermediate CTI representation is a unified format, the extractors are source independent. Next, we describe the design of the extractors. We adopt a conditional random field model to extract security-related entities in unstructured texts. Compared to general named entity recognition, we are faced with two unique challenges. First, the presence of massive nuance particular to security context. Second, lack of large annotated training corpora. To address the first challenge, as this nuance mostly exists in IOCs, we use a method called IOC protection proposed in our other work. By replacing IOCs with meaningful words in natural language context and restoring them after tokenization procedure. This way, we guarantee that the potential entities are complete tokens. To address the second challenge, we programmatically synthesize annotations using data programming. Particularly, we create labeling functions based on our curated lists of entity names. For example, the lists of threat actors, techniques, and tools are constructed from meter attack table. To train the CRF model, we use features such as word lemmas, post tags, and word embeddings. Since our model has the ability to leverage token-level semantics, it can outperform a naive entity recognition solution that relies on regular expressions and generalized to entities that are not in the training set. To extract relations between security-related entities, since it is relatively hard to programmatically synthesize annotations for relations, we adopt an unsupervised method. In particular, we leverage the dependency parsing-based IOC relation extraction pipeline proposed in our other work, and extend it to support the extraction of relation verbs between entities recognized by our CRF model. As a final step, SecurityKG inserts the processed results into the backend storage using connectors. The connector merges the intermediate CTI representations into the corresponding storage backend by refactoring them to match our security knowledge ontology, such that the previously constructed security knowledge graph can be augmented with new knowledge. Since we store the knowledge extracted from a large number of reports in the same knowledge graph, one potential problem is that the nodes constructed from different reports may refer to the same entity. We made the design choice that, in this step, we only merge nodes with exactly the same description text. It is possible that nodes with similar description texts actually refer to the same entity. For those nodes, we merge them in a separate knowledge fusion stage by creating a new node with unified attributes and migrating all relation edges. By separating the knowledge fusion stage from the storage stage in the main pipeline, we can prevent early deletion of useful information. In order to facilitate knowledge graph exploration, we built a web UI using React and Elasticsearch. The UI interacts with the Neo4j database through a Neo4j.js driver and provides various functionalities to facilitate the exploration of knowledge graph, which we describe next. We built features to simplify user view. The user can zoom in and out and drag the canvas. Node names and edge types are displayed by default. Nodes are colored according to their types. When a node is hovered over, its detailed information will be displayed. We build features that facilitate thread search and knowledge graph exploration. First, the UI provides multilingual query support so that the user can search information using keyword or cipher queries, which enables the user to easily identify targeted thread in a large graph. Second, the user can drag nodes around on the canvas. The UI actively responds to node movements to prevent overlap through an automated graph layout using the Berners-Hop algorithm, which calculates the node's approximated repulsive force based on their distribution. The dragged nodes will lock in place, but are still draggable if selected. This node draggability feature helps the user define custom graph layouts. Third, the UI supports intergraph navigation. When a node is double-clicked, if its neighboring nodes have not appeared in the view yet, these neighboring nodes will automatically spawn. On the contrary, once the user is done investigating a node, if its neighboring nodes or any downstream node are shown, double-clicking on a node again will hide all its neighboring nodes and downstream nodes. This node expansion collapse feature is essential for convenient graph exploration. So here's a live demonstration for the UI. So here's a random subgraph sampled from SecurityKG to prompt initial exploration. Let's say security experts want to investigate ransomware called WannaCry. With our system, they perform a keyword search and get a malware node as the search result. By clicking on the node, they can do inter-node navigation to explore the neighbors of this malware node and get more details, such as the security blogs and news that report this ransomware. And naturally, these blogs and news can be also further investigated. In addition to the trivial reported in relation, SecurityKG also captures the threat actors and the shared techniques mentioned in different security sources. The NLP pipeline in the system analyzes the different relations between these entities. We also support cipher queries so that the user can perform fine-grained investigations on the graph. In conclusion, we have presented SecurityKG, a system for automated OSCTI gathering and management. SecurityKG uses a combination of AI and NLP techniques to extract threat knowledge from a large number of collected OSCTI reports and constructs a knowledge graph to structuralize and persist the knowledge. SecurityKG has potential to empower a variety of security applications. In future work, we plan to connect SecurityKG with our query-based threat protection system to enable knowledge-enhanced cyber threat protection. Thank you for your attention.